So what we did is we started by developing a new soft and extremely stretchable material. And then we used a 3D printing technology called stereolithography, where we have a liquid resin and we expose it to UV light. Wherever it's exposed to UV light, it solidifies, and then we repeat this in a layer by layer fashion to build up 3D parts. So what this allows us to do is create complex geometries from our soft and stretchable material, which is pretty cool. But we thought about it, and we all know that traumatic brain injuries are a huge issue. The stats are a bit sobering, but one that sticks out to me particularly is that 15% of high school students reported concussions in 1 year from sports and recreation-related activities. And that, I think, is stunning because, one, we know how damaging concussions are now. We know how damaging they are to developing high school brains, and if it's sports, it's likely preventable in a way. So we ask ourselves, could we use our new material and 3D printing technology to help protect those brains and reduce brain injury? So we came up with a pretty simple setup. We have a brain-like gel. This soft gel mimics our brain, and then we drop a metal ball on it to simulate an impact. We have a high-speed camera and a force sensor, which measures the impact, and then this is our control case. There's no protection. Then we add our 3D printed truss structure to see if it reduces the severity of the impact. So what this looks like is the impact on our soft brain-like gel. It squishes, and if that was your brain, you'd probably feel pretty bad. So then we add our truss structure, which deforms and helps dissipate the energy, which protects the brain-like gel. So when it's protected, we'll look at that high-speed camera, and it's less severe. But you might not believe me, because it still looks like an impact. So we'll take our high-speed camera data, and we'll pull out the position of it over time and look at some of the numbers. So this is what the data looks like. This is our normalized height over time. So you can see it impacts, and it deforms, and then it rebounds. But what's so important for brain injuries is acceleration, so how quickly that impact happens. And that's what we see here. It accelerates downwards very quickly and then back up. So let's add our protection structure, this 3D printed soft material. And so the deformation is less. It's not much, but it's less. But what's so important is it's slower. That deformation is happening over a longer time, which results in lower acceleration. So let's talk more about why acceleration is so important. There's two parameters here that are critical. The magnitude, how much acceleration, and the duration, how long it lasts. So why that's so critical is what's called the Wayne state tolerance curve. Brain damage is a product of both magnitude and duration. We can withstand very, very high accelerations, but only for a fraction of time, whereas relatively minor accelerations build up over a long time or long duration can cause injury. So there's some examples here, but we need to account for both duration and magnitude to see will we get brain damage. And that's what our modified head impact criteria does, and when we use this parameter that accounts for both variables and when brain damage will occur, we see our protection truss is 25% less, at 75% less severe, 25% of the no protection case. It really, really protects that brain-like gel. So to summarize here, we did a lot of work developing this new class of soft materials, and we did a lot of work making it 3D printable so we could get these architectured and designed 3D structures. And the combination of them both produced these structures that can protect brain-like materials and really reduce the severity of head injuries. So we're very excited about the potential and continue to translate this research to the real world.